Maybe a few words about myself. I'm Markus Neteler. I'm in the, let's say, open source business, movement, whatever you want to call it, communities for a long time. I started back in, I think, 1993 to use GRASS GIS. As a student's helper, I got exposed to this software. They put me in front of the Sun workstation and said, okay, look, we got to know this software. It exists. Please learn it and tell us how it works. And back then there was no manual existing, only individual description of commands, but nothing which was a comprehensive tutorial. And so that was the way to start. And since some of you at least are students, I can only encourage you to just pick the tools you have seen this week and play around, because they are really powerful. I discovered that my lifetime will not suffice to even start half of the tools we are seeing here, but it's worth it, and there are plenty of possibilities. I was working in research myself from 1999, but from 2001 to 15 in Italy, and then I moved to Bonn. So we started or created a startup there called Mundialis, and we are dealing with open source software, with open data. We are doing massive data analysis. We are lucky users, happy users of the Copernicus Sentinel program, for example, and our scope is to turn these, meanwhile, petabytes of data into information which are useful for different businesses, also for research and so on. We are also a partner in the OpenGeoHub project. I think Edza will tell tomorrow something about it, or today, I don't remember, today. So later today he speaks about the OpenGeoHub Horizon 2020 research project. We are just doing some back-end stuff there, but it's quite interesting to work together on also this kind of topics. Yeah. Okay, so back to the stuff. Yes, I forgot to mention that I'm quite involved in this GRASS development, of course, so I'm more or less coordinating the development since 1997, so long time ago. I got meanwhile also elected, so it's not only self-promotion there, but it's really about doing stuff. And we already had some talks here, how you can get involved. So if you're interested to contribute, and contributing means not only to code, but also to point out things which you think are lacking, or bringing in new ideas, writing some documentation, bring in examples, new sample data, whatever you can imagine, everything is welcome. So I would now like to show you the overview of what we are going to do here. For those who are familiar with GRASS, it will be quick, some GRASS GIS basics. Then I brought some sample data you hopefully downloaded. If not, you can still do, because the Wi-Fi is super here. And I'm using the ECAD climatic data time series. That's a project providing European climatic data at daily temporal resolution. So we are having data from the 1st January of 1950 up to, I think, mid of 18 now. So it's really fantastic. And if you want to do time series analysis, that's a nice playground. Yeah, looking a bit into some simple data analysis, a bit of zonal statistics, machine learning. Of course, I will not dive at all into machine learning here, but I show you how to make use of one add-on, which is which got implemented. There are different add-ons doing machine learning. There's also an interface to MLR, for example, and so on. Yeah, and then a bit on linear models and RS again. So I assume that we won't get there, but just to let you know that the stuff is there. So I hope everybody has the GRASS 7.4 or later software installed. We support any operating system. So if you're on Windows, Macintosh, or Linux, or supercomputer, cluster, cloud, whatever, it's fine. You can use that. I have here put a link with the different details here on installation. So software download, Windows, Macintosh, Linux, some references, and some other tutorials and so on. So nothing we need to look into now. And course data are prepared. There's the ECAD elevation file, a GeoTIFF here. So of course well, it's a kind of ridiculous example. It's an elevation file in GeoTIFF. I just want to show you how to import that so that you know how to do it in future. And then for the rest, because it's not that exciting job, here's a GRASS GIS location, which you please also download and put somewhere. So this somewhere I have even defined. The first file, just to find it back, you could, for example, put into your home directory or the, what is it called under Windows? I don't know. My Documents, something where you find it. Make maybe a subdirectory geodata and put it there. And then the other one, the second file here, you can put into a new folder called GRASS data. So it doesn't need to be GRASS data, but in all the documentation it's called GRASS data, and so it probably makes sense. I've done that already. Oh, the font is maybe too small, is it? Sorry, I forgot about that. And now here, press. You over there, can you read this? Yeah. So there's one, I have now one directory, geodata. There's this zip file, and I unzip it simply. So I also put the reference inside, where I got this data from. This is ECAD version 17 from published this year. Here's the link and the citation. Okay, and then, where I'm here. So in GRASS data, there is this other file, which you also please unzip. And it contains a bunch of subdirectories. That is the so-called GRASS database structure. I will say something about it in a moment. So what you can see here is that, okay, something is wrong with the window size. Wow. Okay. So you see already aggregated data. I told you that it is daily data. I have done the job for you. We are speaking about a multi-gigabyte data set, and I didn't know what to expect in terms of network here. And I know that not everybody will download stuff already at home, so that's why things are aggregated here. Okay, now you're more or less there, I believe. Some basics. Some basics you find here in this sub-page. So we believe that GRASS behaves like any other GIS. What does that mean? You can process the usual data and so on. There's only probably 2 or 3 specialties there, which not every GIS provides. And one is, for example, the processing of massive data sets. So massive, I mean like time series, which are, I don't know, in the billions of pixel range. It's okay, you can do this with this kind of software, even on a decent but not supercomputer hardware. And you can also consider, and this is something which I really suggest, and especially after this week, you pick the tools which do the job best. Yeah, there is not the one software which does it all. So I don't think so that it exists, but you better go where the tool is good, and then it saves your time. So geospatial analysis, analytics, and we have also vector topology. This is quite special. It used to be standard in the 70s and 80s, and then in the 90s, let's say some larger GIS company decided that it is not needed at all, and so they kind of dropped it. GRASS was started in the early 80s, and we never dropped topology, so topology slowly comes back, and we still have it, and we spent years on improving things. So you can, if the only usage you do is to fix your broken vector topology with GRASS GIS, you are welcome to do so. You can, by the way, do it more or less in a single line of code. So, concepts of GRASS GIS database. You remember you just extracted here some zip file which comes with subdirectories. There's a reason for doing so. In the end, there's nothing complicated behind it. It is a directory structure which is standardized, and the users should not edit manually inside, but use the GRASS tools to do so. I think some of the formats, like the GRASS raster format, it's an own format, should have become a standard like GeoTIFF is. You know, GeoTIFF has some limitations. It cannot store a color table with floating point numbers and so on. This GRASS format does it all, but as I have written here, they probably missed, or for political reasons, they didn't manage to get this format standardized through the Open Geospatial Consortium. Okay, now we are like 2 decades later, and maybe it's too late, but anyway, this format comes with some advantages. And the vector format is also an own one. For the attribute management, by default, SQLite is used internally, but you can also connect to PostgreSQL or whatever you like. The geometry is stored in GRASS GIS itself because it's topological. Do I have an interface to PostGIS? It's bidirectional, but there's some point in keeping it inside. So you can probably say we have the external formats, which is GeoTIFF, whatever raster format, HDF, Net, CDF, and so on, and the internal raster format of GRASS GIS. Same thing for the vector data. External shapefile, geopackage, whatever, PostGIS, and internal is the GRASS vector format. So just this distinction. And then more or less the last special thing here, computational region. This you will see also later. What is the idea about computational region? So imagine you have this kind of map here. So that is North Carolina elevation map. And this could have, I don't know, for example, you have a 1 meter LiDAR scanned elevation model, so this will be quite a few pixels. And now you get a GeoTIFF file with this data set, and then you only want to calculate some small portion there. In most GIS, you have to basically deal with the entire file. In GRASS, it's a bit different. You can either import it with the advantage of color table, blah, blah, what I mentioned before. You can also alternatively just register this map inside GRASS. This is done internally through GDAL, which means it puts a link to the external GeoTIFF file. So it takes 1 nanosecond and the map is visible. But then the concept of computational region starts, and you say my active region is only, for example, the small boundary box which you see there. And all the subsequent computation is done there at the resolution you want. So this is quite interesting also for global data, which can be quite heavy. Yeah, and then you just operate on this tiny portion. Super easy. So data management, I already mentioned, we have this GRASS data folder. And then we have something called locations, usually, or project folder, you may also say. And the third thing is map set folders. So what does it mean? GRASS data is this simple directory just created. And inside that we have directories. Already at this level, the directory is created through GRASS GIS interface or command line, up to you. That means one project in a GIS context usually consists of a projection, for example, let's say UTM something zone, which requires metadata. So you have to say what is the EPSG code, for example, or the projection string in order to create this definition. And everything which is inside belongs to this projection then. So you already understand. You can technically write all these internal ASCII files and describe the stuff, but you can simply use the interface, which does it for you. Inside are the map sets, and the map sets are for organizing your work. You must know that GRASS is even a multi-user system, so if you install it on a network drive in the institute or in your company, all the people who want to work on it just run their own session, but connect to the network directory, which contains this GRASS data, and everybody can happily work in parallel. And in order to avoid that one user is overwriting the stuff of a different user, you can, for example, at map set level say, this is the map set of this person, and this is the map set of that person, and all this access control is already happening. So this is really nice for work groups to avoid that you have 15 times the same data, but unfortunately they differ a bit because someone did it this way, the other one did it that way, and you can organize data like that. So just again, and that's more or less it about introduction then. You have the bunch of too many different GIS formats. So luckily GDAL exists and supports them all. And we of course make heavy use of that to do this import-export stuff. And then we have the GRASS structure here. Okay. So we will now just import the elevation map we have seen before. And just so, well, this I will not go through now in detail. These are the different commands which we are using in this session here. But what I could do is simply show you some of the functionality before we really start. So in the GRASS manual, there's a keyword index. And this, all this stuff is, by the way, automatically generated. So the manual is automatically generated except for the text descriptions, but all the combination of what you have seen before, like in this random example here, you have the name, a one-liner, what it does. You have clickable keywords here, which bring you to this keyword index. Now it jumps to projections. So these are all the tools which deal with projections. You get this overview. Mandatory is without brackets, optional is with brackets, and flags and parameters and so on. And the nice thing, you know, many developers do not like to document. So we decided long time ago, okay, let the computer do the job. We extract from the source code all these descriptions automatically, and we only have to write this text part here. And then it is, during the compilation, it is all put together. And that's it. We have also the source code link here, so you can always jump to the source code. This is, for example, a Python script. So this is just for those who are interested in coding. We have some block on top, and then we have a standard definition here. And this works in Shell and in Python and in Perl and in I don't know what other languages. You see this magic here, this hashtag and %. And this is then parsed automatically after all this description in the parser. So this is happening here. And this then generates the manual which you have seen before. So this is some quite convenient magic here. So in the history of development, you can also find what has happened, who has done what, and so it's fully traceable here. And yes, maybe one day we move to Git, but we have something like, it's already on GitHub, it's mirrored on GitHub, but we have something like 35 years of development to move over, and it takes a while to get it done the right way. It's ongoing. Okay, but back to functionality, that is why I was here. Just take a look at the key, can you read them? look at the keywords. So from evapotranspiration to data aggregation, map algebra, albedo, what is that? Binning, data binning. This is something for LiDAR data import. You have a huge LiDAR cloud, and you want to, in one line, you want to have a raster map following univariate statistics. You just take this R in LiDAR, for example, and it will do this binning job here. You define your pixels, and all LiDAR points which fall into this individual cell will be considered, and then you have a bunch of options to trim, to filter outliers, and so on. And you can calculate all these measures in one line. So there are quite a few nice tools here. Classification, cloud detection. We just got through Google Summer of Code the Sentinel cloud detection. I think it will show up soon here. Yeah, it's an endless list of stuff you can go through yourself. Okay, so now let's start. I think here are at least maybe 5 different operating systems in the room. Just kidding, no, but you will manage to start it up yourself, I hope. I'm a command line junkie, so I will do that. GRASS 474. The first time you may want to say minus graphical user interface, and then it will bring up this screen here. If you did not unzip this ECAD, I'm sorry for those over there. The font is, I cannot enlarge this font now. Is it doable for you? Yeah, hopefully. So what do you have to do? You have to go to the directory where you have put extracted the data. So I selected GRASS data here. Where is it? Voila. So here must be GRASS data, and then it should automatically discover all the map sets inside. For you now only one. If you are, this is my real one, yeah, there are of course plenty of them. Okay, I'll go back to this costing here. And then the next step is we want not to confuse own data and official data. This is something especially important in science, so I really recommend that to separate your own stuff from that you have received. Otherwise, after 1 year, you will not remember which is what. And here these map sets are allowing you to do so. So I write, for example, user 1 here. You can write whatever. You write your name, I can write Markus. But I think in the tutorial I used user 1. So now you have technically a new directory inside. And if you go there, then with start GRASS session, then you are in the system. So this is still, and to be honest, I would modify that. The strange thing when you start GRASS, you get presented this screen here, and now what? Yeah, but just accept it for today, and then we'll see what future brings. By the way, here's also a download button, and here you can download different sample data, which we will not do now because we may kill the Wi-Fi. But you can, like this, on a new computer, just fetch the sample data automatically, and they get extracted, and you are fine. Okay, so now you get, okay, these warnings you can happily ignore. You are in GRASS GIS. What you see here is basically 3 different screens. One is the menu stuff. This will get the kind of legend. Here's the map display, and here you have the command line. The command line is basically interesting So this separate window is basically interesting on Unix-based operating systems. You also have the same command line here. I will show shortly. So back to this text here. We have GRASS data. We set the GRASS data. We pick the ECAD location, and then we should be settled for now. By the way, if someone has a problem, Vero is here. For example, just shout or signal, and then she can assist. Okay. So now we'll take a look at this stuff here. We want to load a vector map. There's already one vector map there. Here's an icon called Add Vector Map. It's somewhere in the middle. And from this dialog, you can pick the one and only map which is there. And you should see a world map. This is the natural Earth data set. Okay, fairly easy. And then you see it here in the menu. You can double-click. You get back to this dialog. You can put I don't know, random colors, for example, in the Colors tab, and it should colorize. Where's my window here? It should randomly colorize that. You can do, of course, a bit more decent stuff here, but you can discover yourself. So with in the map itself, you can zoom. So you can also obviously query the map. Here's a query tool. And you click into, where are we now? Somewhere. Sorry, you have to pick it from the legend first. So this data set is quite rich. There's all kind of attributes here, like how many people are living there, what is the BIP and other stuff. Okay. So I've written here about this organization. First steps with a known data set, we have already done that, called user 1 in this example. And the point is to separate the original data from our own analysis. One detail, what I want to show you is when I click here, you see that it opened this dialog window here, right? Technically, this is generated on the fly. So this user interface is just generated from the code itself. What goes into the manual, we use at the same time to generate the user interface. What does it mean? For example, I have picked here under required this map, and then I picked random colorize. If you look down, here you can see there's the command line. So this user interface does not do anything else than constructing the command line. Here's a copy button, and this copy button is copying it into the clipboard. And then you can put it somewhere, for example, here, paste. Okay, hard to see now, but you can imagine. And it would print the stuff. So if I write -- HTML description, so nothing you need to replicate, it comes out as HTML description. If I write -- interface description, yeah, we get the same thing in XML. And from this XML that's parsed automatically, this user interface is generated. So if you now think about it, minus script. So who wants to manually write all this description here? Not needed, because you can, if you write your own stuff, your own code, for example, you can just recycle things from a different one. So I wrote minus script, and it comes out in Python this time. So it even writes a description there with my current username on this computer here, current year, the GNU license, and all this is already done. And if you then want to do your own command, you can just auto-generate this, this code here and put it into your own Python script or shell script, or it's all the same, Perl or whatever language you like to write. Okay, so this so much for scripting and for this command line here. Yeah, I have some annoying library debug message stuff here. Sorry about this. I try to hide it. So we have basically this circular, not dependency, but circular fanciness that we can write on command line. From command line, the user interface is generated, the manual is generated. You can generate descriptions, which you can then recycle for your own coding. And this is the approach we are using for quite some years now. Okay, so much for this, this part here. So now we want to do something more. You do not have to restart GRASS unless you are not yet in this location here. If you don't know where you are, it is written on top of the map display. Yeah, there is the name of the current location. So one session means we are using one location or one project at a time. You can have multiple sessions open which do different things, something we commonly do in cloud processing. So each job is one setting, that's no problem. So you can open as many sessions as you want, as you have memory on that machine. So on the command line, I think I will now not use this one here, but I will use the one which is integrated in the graphical user interface. Here's something written which is called console. Here's a tab layer, you have seen that before, console. Then the third one is modules. Here you can see what functionality is there. You can expand it, or you can search for, let's say, a watershed, I write, and you hit enter, and it jumps to one, to the next, to the third, so everything what is dealing with watersheds. Or you write topology, plenty of stuff. By the way, time topology is also there, so not only spatial topology. You have also a data explorer here, so you can see what maps are in this inside here, so you can just navigate, take a look. You see here the precipitation time series. So we see funny color artifacts here. The reason is that I didn't clean the display before. Where's the clean display button? What? So somebody removed the icon erase display. Why? I'm blind. Sorry, it's usual. If you're on stage, you don't see anything. And from this angle, you cannot read that. So I'm a truly command line junkie. Yeah? I don't know this.
So just unclick whatever you don't want to see.
Okay, thank you. I'm not teaching anymore, so that's why. Lucky me, right? That's why I went to a private open source business. No, just kidding. Okay, so this was the data tab here. And then, hurrah, there's also a Python interface, and it's already in the GRASS session itself. So that means, but Vero will show something later on this, so I will not dive into Python now. Please go back to the console, and then we can start. So I'm here in chapter 2 now. In case you are lost, I'm here. And we look at the available data. So I type here g.list, and you see it's context sensitive. It shows you also the options. Type equal raster. You can then hit enter. And it doesn't show anything. So, does it work for you? How about this? Okay. So I was typing basically the first command here. So we didn't get any result. As you see, I'm not nervous because that's what I expected. And I wanted to show you the concept of map sets. Map sets, you remember, that was this subdirectory structure. Here I see I run gmapsets -p, and the result was user1, that is the map set we are currently using, and permanent. This permanent map set is the one which we are using now. So this is the ECAT something, and here we are in user1, maybe here, user1. There's nothing inside. There's one which is called permanent, and it is always there. This I didn't mention yet. The permanent map set contains the metadata about projection, resolution, and whatever, database connection, I don't know, other stuff. That's the place, the map set, where you could put the base cartography. For example, the project elevation maps, street network, whatever you have. Because the idea is permanent is visible to all the other map sets, but if you are in this map set, if you are in this map set, you see permanent, but the other map set you only see if you activate them. And this activation we will do now by simply listing what map sets are available, g.mapsets. Careful, there's also gmapset without s, which is a different command we don't use now. -l, it lists the available map sets. Available means it's on the computer, but not necessarily visible to you right now. So we were in our own map set, user 1. We want now to add the official data, map sets, the one map set equal ECAT 17. And operation equal add. I can also scroll back by using the up and down arrows and go twice back to the gmapsets -p. And now you will see that also ECAT is listed because we said put it to the search path. And I go 4 times back, I think, and I can recycle from the history this glist raster command, so that is this one. And now we see the maps which are in the ECAT directory. Or map set, better to say. You see the difference? So nothing complicated. You must imagine you work in so I did that for a long time in a work group. All the group members worked in this network drive. We had something like, say, I don't know, 50 locations with hundreds of map sets for all the different experiments and maybe papers and whatever happened. Yeah, in order to not get drowned in the thousands of maps, Yeah, this location map set structure got invented already, by the way, in the early 80s. And it feels like useful. Maybe it's now why this confusing for you, but as soon as you dive into time series processing, you need some structure, otherwise you get lost. Okay, the country borders, I will just show you, and you don't need necessarily to do that. Honestly, I didn't try this in this window here. Can we define variables here? No, we cannot. So this only works in this real command line here. I show you from the text file, okay? What I do here is to define a variable. This is a terminal shell variable in order to avoid a super long command here. Yeah, that's all. On Windows, this will not work necessarily. So you just copy, don't do this now, but just to tell you, you put this string here and it works equally good. So what is this stuff doing here? There's one site which is called Natural Earth Data. You know that maybe? Interestingly, I lost the colon there. So if you go to, what's wrong here? No, okay, I try again and put the colon into the right place. Magic.
That's not the whole link, because they use like naturalerth.com, naturalerth.com.
Did I lose something here?
No, the link is, there's the natural earth twice. You'll see that in a second.
Okay, I try from here. Ah, yeah. Okay, yeah, this is the magic of this website.
Yeah. I asked the author once, and he said that he set up the page like many years ago, and
it doesn't bother.
Yeah, it's like it's a mess to change that again.
Okay, I mean, I knew this some days before when I updated the tutorial, and now I immediately forget. So they have this funny situation to have it twice. Yeah. Never mind. Just copy paste in case, and then you are done. So now the next one is to run vimport. I do it for you. And this is now doing this amazing thing, which is provided by OGR and GDAL, that you can download data directly from the web. So we are doing this import. This is standard import command. It was written for shapefile, geopackage, and whatever stuff. Using the VSI curl driver, it downloads the zip file, and using the VSI zip driver, it unzips on the fly. What you can do what you can use that for, initially also I had prepared some SRTM exercise on the global 30-meter SRTM, which you definitely want to download completely because it's 200 gigabyte GeoTIFF file. You can just extract a portion on the fly by setting the computational region. You remember we can zoom to some portion and say this is my active area, and then extract on the fly from this world map, which is sitting on a server somewhere, only this tiny part, and you are done. So that's quite nice. Okay, so what happened? Something happened here. I scroll back. vimport is fetching this through OGR, fetching this file, unzipping it, and you see OGR extract checks what's inside. There are polygons inside an attribute table, and it processes them. And up to here, it would maybe up to here, it would be simple features, but you see here also centroids being treated. And then the GRASS topology engine starts and checks if the topology is clean or not. This always happens. You can switch it off, but normally you want that. Only in case of laser scan points, for example, no need to do that because points are points. So it does a lot of jobs, checking for duplicates, double boundaries, dangles and whatever nightmares you can have there. In broken data, assigning centroids, it checks the area, it checks if everything is fine. So building topology is done. For those who are a bit more seasoned, like some of us in the room here, who have seen ArcInfo, for example, they remember this procedure from ArcInfo. Same idea, same, more or less, maybe same technology, I don't know. But we have been continuing to develop it. So we have some really good programmers who spend years on topology, fixing topology automatically, and this is quite nice. So the map came in, everything is fine. We have centroids assigned, we have areas constructed. An area is nothing else than a boundary which with a centroid inside. So this is this topological construction. And we have some islands there. Islands is like a hole. You do not have a centroid there. Successfully imported. And this v-import, it does also the reprojection on the fly. For example, you are sitting in, I don't know, some other Mollweide world projection, or the, from my side, not so much loved Google Mercator projection. Then you just set the same command. The original data in latitude, longitude, they will be reprojected on the fly to the current projection you have in this location, and the topology is also checked. If it's totally broken and you can't fix it, then there are tools. There's one question. If, or is it for me or for her? Okay. There are tools to do operations on vector topology. There's also an interactive digitizer, but there's also a command line digitizer with, I think, Python interface. So if you want to do like operations, topological operations on command line, no problem. So next step is, we remember we got a geotiff file here. I will skip this now because it's too easy to do. There's rimport or rngdal. You can import the thing. You can then assign a color table, and we are happy. Okay, I skip that. So visualizing maps. I will also skip because of time. I leave it here in the, it is there in the tutorial, and legends and stuff is here. Sorry, here on top of this display. You have a choice, raster, vector, legend. You can draw a histogram alongside the legend. Maybe I just show that one as an example. So I go here to gradient, add histogram to smoothed legend, and here you go. You can move it around with this pointer here, and if you want to modify it, you double-click it, and then you come back to this dialog. So it's also written there, by the way. And right one is remove the legend if you want to get rid of it. So I think the elevation map is really already there. We have also here another selector. Okay, I remove everything here from the list. Ciao. It's not deleted from the database, of course, just from the legend. And here's a tool which is called add multiple ones. And here you can switch between raster. I didn't mention, we have also volumetric data management, voxels, or whatever you want to call it in your language. Yeah, it can be cubes or it can be rectangular. It's up to you how you shape them. To describe, for example, atmosphere, multi-layered atmosphere, or soil, or whatever you can imagine. So we can handle that as well. And we can also get from, for example, slices of different soil layers, turn them into a volume, or the other way around. So I wanted to have raster here. And here we can switch again between the different map sets. And in ECAT, unselect all and take the first one, we get the elevation map. But here, importantly, you have to activate it. Okay, first I have to close this. So what I did, I repeat, I went here to this icon at multiple raster vector layers. I keep raster, I switch to ECAD, select or deselect everything, and then I pick the elevation map, and then OK. So, and it shows it here. Now you see the resolution on my display is lower. This is because I did something before. Here's So in the context menu on the legend, there is set computational region from selected map. Remember computational region, the active area. I want to be sure that, if I want to be sure that the entire elevation map is used, I can set it from the map. If you want to do the contrary, you zoom in somewhere and you want to say, okay, this is my, maybe, okay, with the low resolution data, it's not that exciting, but still, you can do the opposite, set the computational region from display. Yeah, so you can switch back and forth. I will not do this now. Okay, and then you can do stuff like that. So now time to look into some data. As I mentioned, I did all the aggregation already, which was a kind of aggregating to annual data, and then I was calculating these 30 years summaries or averages for 2 periods we have meanwhile. That's nice for comparative analysis, of course. We have mean annual temperature. There is more, and we have minimum annual temperatures there. And now you could please try this exercise. I must tell you that this part only works in Unix-based systems. So this is a kind of separate monitor here, d.mon. Yeah, it will bring up a separate window. It looks the same as this one here, but it comes from the terminal command line. On Windows, I think it does not work. So on Windows, you are obliged to use the GUI here and the console here. So this console directly communicates, this console here, communicates with the display here, while this terminal shell window here communicates with this separate one. So I want to see what maps are there. But in the first place, this I put throughout the entire tutorial. Be sure that your computational region is right. I will use this window here because you can better read it, okay? So what I did, I used the gregion command. The gregion command is used to manage the computational region. I say I want to set it from the raster area here. From this raster map here, and I want to print. So once again, if I don't do -p, then it doesn't print what it does, but I like to see what happens. This is latitude, longitude, and we have 15 arc-minutes resolution. This is the default resolution of ECAD. We can also put -g. -g is everywhere. We standardize it a lot. -g is for script style output. You get a variable equal the value, and it comes in decimal. And this is then also parsable. So you can parse this in Python or in Shell and so on. We can do by the way, we can be in any directory here, so there's no need to stay in GRASS data. We can do pattern matching. glist raster, I write pattern equal, and then something with wildcards. You can also have regular expressions here. See the manual how to do that, and you can do all kind of fancy stuff, whatever regular expressions can do. So we get an overview how many precipitation maps we have. So they are split into monthly summaries over 30 years. And now we can do some processing of time series. How many window users do we have? 40% maybe? To be honest, I didn't try this on Windows. So I will show you a bit more fancy command now. Maybe I separate it out into this here. So what happens? I split it into different lines so that you get an idea. This is some, let's say, trick or whatever you want to call it. Is it readable like this? So rseries is the command. Yeah, input will be the list of maps. This is what I want to feed into this aggregator here. Output is what is the name of the output map to be done, and methods is, of course, what I want to calculate here. So now you want to know probably what kind of methods do we have. You can write gmanual rseries, and it will pop up the manual page. And this aggregator here can do all kinds of stuff. You can calculate, for example, I mean, the standard thing I don't want to explain, but we have, for example, counters. So imagine you have a stack of raster maps like these 10 here, which you have seen before, and you want to know for each pixel in this stack what is the highest value. So you would use the maximum operator, maximum method, but you also want to know in which month does it occur, actually, in this individual pixel stack. So you additionally use the count, and then it will spit out a second map, which you count max occurrence, what is the max first occurrence maybe, and it will contain a number of the map in which the maximum appeared in this sense. So you can imagine now all kinds of combinations, what you can do. So you can hunt in a time series easily without even doing time series management for the occurrence in time for each individual pixel stack. So you can find here all the descriptions and so on. Okay, the question is now, how do I feed all these map names into it? And of course, I'm not willing to type anything here of all the map names. That's why we use the output of the pattern checking as the input to r.series. So I just copied out this one. So remember we had this. If I add separator equal comma, then I get it a comma separated list, and voila, we have the input ready. Since I still don't want to copy paste that, I use this nice trick here. Carol, does it work on Windows? Do you know? Backticks? Sorry? Yeah, it doesn't matter. It's not a problem. So we solve it. Windows users, please see below. Yeah, you first run this. Copy, paste. the output then into our series. Paste. Yeah? And the rest is the same. So the Unix-based people here, yeah, is it clear? More or less. The Unix ones can use a nice shell trick, which is the backticks. I know for a few keyboard languages how to find them, but not for all, for sure. Importantly, the backticks go from upper left to lower right. So in case you have never seen backticks, it's sometimes there's a key on your keyboard likely where you play with the shift and it will come out. Maybe you have to hit twice. And what happens then? This command is executed first and the output is sent to here. That's all it does. So I now execute it here. So input, this one, dong, ready. So we aggregated it. Pretty fast. Okay, we have only a few pixels here, but also for large data sets, it's fine. So I show it once more for those on Windows. You first execute this one, then you pick here the output, copy, r.series input equal paste. Oh, too fast, sorry. No, bad. Oh, come on. So it seems I copied some junk. We can do a different trick. We can also define, so another option is to define output here, and you write the output to precip underscore list dot. It's not really a CSV file, so what extension I do? Data. File. So instead of input, you use then file. And the rest is the same. So maybe that's the safe way. Okay, so I assume that you have were able to do this. And of course you can continue here. We do the same essentially with the temperature map and look at the stuff. So eventually you would get something like this here. I have to look a bit at the time, right? 15 minutes left. Okay. So the scope of this morning session was not to do cool rocket science, because no time for that. And for sure I brought stuff like half a day or 1 day here, but to get you into the, let's say, initial feeling how to use the tools here. That's all. So this is the aggregated mean annual temperature. With the time series tools you see later on, it is even easier to do that. But I wanted to show you some basic commands here. So maybe I just present the rest now, if you are okay with that, just to give you an overview what's there. And I will give some comments here and there, or I show it here as well. I need to, just to be able to show you exactly, I need to quickly execute that. So this is done. Color table. We have color tables, which are really nice. It's open source, feel free to borrow them. And you can see here that some are not properly shown, wow. But in any case, help button helps and, oh, cool. Okay, something went wrong. Usually there's always a color bar showing the different color tables. And the point is that we have a lot of thematic color tables there, like population map with logarithmic scale, like precipitation millimeters, like Celsius, Kelvin, different elevation color tables and so on, which have been tuned for being nice on flat areas and so forth. So the temperature I didn't do yet. That is this one. So then we can show univariate statistics here. We always take some time to check if we get the same results in R. Of course, R for statistical analysis is kind of gold standard. And importantly, let's say the different implementations should agree on the same result. So what you get here, this is extended -E, extended statistics, so you get also quartiles and so on. And -G means, again, script-style output, which you can parse. Parsing means if you want to feed the output of such an analysis, and I'm always thinking of a scripted way of doing things, like it is common in R as well, we want to fetch the results here and put into the next command. Advantage, you define maybe on top the name of the map you want to process, and then you can cycle this script forever for all kinds of other maps as well. So if we want now to for example, to analyze some data of the Czech Republic. You remember we got the country boundaries. And here are, with VDB select, vector database select, we can check the attribute table even in the terminal. Of course, we can do it in a table system as well. And I only want to see the first 5 rows here. These are all the colors. You see it's pretty rich. And this pipe command here is again a Unix thing. With that I can grab in the huge list. So if I print everything, it's long. I can grab only Czech Republic line because I want to know the ID of Czech Republic. I can also use a where statement for that. Where. So of course I don't remember what the column names are. -info, show me the different columns. -C, map name. Displaying column types and names for database connection. And now I see here somewhere the, what is it called? Admin, I think. Okay, this one. where column name equal, and since it is a string, I have to write it like this. Apparently it is not exactly written, or it's in a different column. That's why I love Unix tools, because then you can just use this command and you find out it is ID 50. And now we create a raster mask to mask out only the country we are currently in. And now you see here a change, raster mask present. So I think if I display. Yeah, so I just re-render here. And you see the area is the entire one, but we only see Czech Republic now. Few pixels because the resolution of the ECAD data is low resolution. But now all raster operations are done only here. We can even no, we don't show this due to time. And if I now rerun this univariate statistics, since we did not set the computational region to only Czech Republic so far, it is showing the entire Europe. We have a lot of no data areas there. Sorry, here. A lot of no data. That's why the null cells is almost 100,000. But the statistics are applied only to the active pixels here. Yeah, so it's very easy to subset with a random arbitrary shape. If I want to get rid of the mask, I do -remove. Mask is gone, and so that you don't forget it, there's always this. I activate it again. There's always the change here, and in the display, there's written mask here in red. In red color, so you know there's a mask active. Okay, I remove it. So we can do all kinds of calculation now. This I will not calculate. This is map algebra. Maybe I put it here so that you can better read it. We are doing the differences of the aggregated annual data of this time period with that one. So we get out a difference map. And then we have a dedicated differences color table here. And we can look at the statistics so you can observe. So there's a mean difference of 25 millimeters here in precipitation over these 2 blocks of 30 years. Zonal statistics is also pretty easy because the univariate statistics accepts a zone parameter. So you can give it, for example, a country map, and then it will do all the univariate statistics separately for each polygon. And then you can do whatever graph you want. Okay, not so much time left. I will go through the next topic, the machine learning, without saying anything about that. The idea was to, I don't know, if you know the Köppen-Geiger classification scheme, that's pretty old, 100 years almost, I believe. I should remember, but I don't. There's somewhere the citation down there. So I thought Köppen-Geiger is based on some data set which I don't know, and especially I don't have. But my idea was, can we reconstruct in an easy way kind of the Köppen-Geiger zones using the ECAD data set? That's what I try to do here. So I found somewhere in the net this citation, Chen et al. 2013, something like 12,000 points in the world with the associated Köppen-Geiger zone. So maybe just to show you what we are talking about, there was a recalculation of Köppen-Geiger done from this by this institute here. So this is the classification. So I will also add note to self. So this classification shows your main climates, continental, arid, warm, temperate, polar, and so on. So polar here, for example, you can imagine. And then there are different, let's say, subcategories based on precipitation and temperature. So that's quite nice because exactly that we have in ECAD available. We will not be able to reproduce it at this level of detail, at least not in the given time, but I just wanted to try. So I have, once you are back home, here a separate directory which contains the data. Here's the citation or the URL. It's a website where you can find this table I was taking. Again, the data sets here you have already downloaded, and so it looks like this. Yeah, position, and what they found in this period is the Köppen-Geiger zone. Yeah, pretty simple and a huge table. Okay, now I wanted to do the following. It's separated out into a script here. So if you scroll down, you'll reach the script. We extract 1,200 points. Again, it's not rocket science what I do here. We fetch alongside the known points, the table you have just seen, all the ECAD variables. This we can do easily in GRASS. We have to convert the class names into numeric IDs. Then we rasterize this, and then we throw this at r.learn.ml. So r.learn.ml is a nice tool, r.learn.ml. It's an add-on. Supervised classification and regression of GRASS rasters using the Python scikit-learn package. There's the same thing, it's called v.learn.mlr based on R. So more or less the same thing. It's a different implementation, of course. So if you prefer to stick to R, there's another add-on. So, and this is not all mandatory. It's looking like crowded, but the reason is that there are different classifiers available here. Yeah, you can see a huge list, and then you have to pick the parameters accordingly. Okay, what we do here is essentially we import the ASCII files, the ASCII file, the table I mentioned, and then we can look at it, and we extract 10% of random points, for example. You just give the number and separate it into a new map. We look at it again, and then we want to know how many different classes we have. This you can do, for example, in SQL using select distinct command, and since the attribute table is stored in SQLite, you can do this kind of SQL statements. And it would show you 18 classes. And then we join to it the legend. So why legend? Because ETH you can probably remember what ET you mean, or DFC, but maybe you even don't know. That's why I have put here a legend as well. And this legend is kind of translating the code of Köppen-Geiger class to the numeric code we want to use in the classification. We also have the standard colors here from the Köppen-Geiger project. Oh no, sorry, I had to go here. Yeah. So then we fetch the variables, and this is done by the command v.what_rast. So vector what_rast, you query the raster map, you give it the point map here, and you say which variable you want to query. And since we want to do a lot of them, yeah, we use again what we have done before. We use a wildcard and say, okay, all the maps which follow this wildcard here. So this is the different precipitation layers and t-mean layer. So something super simple. Again, I did an aggressive subsetting of the real data set because of space here. And that's why it is so limited. But you can loop over 100 variables if you like. Populate that map with all these values. Additionally, we put in also elevation. You can now think of why not exposition, distance to sea, or so oceans, or whatever you can imagine. And then you go into the business of doing machine learning. But first you have to have this extension. And this extension you can fetch with g.extension. So g is general, like gRegion, another g command. And it downloads this Python script here and installs it, and so we can make use of it here. The last thing before doing so, we have to tell rlearn ML what is the raster stack of data to be used. And for this, GRASS has a command called i.group. It comes from the satellite data analysis to group different channels into one meta object, let's call it. And the same approach we can use here and say all the maps we had for the query we put also into a single group. And then we feed this group into the command, rlearn ML. The output is then random forest classification in case I do this classifier. Here we have the number of estimators and all the important tuning parameters I simply omitted right now. But please enjoy the manual page. Here's plenty of stuff you can look at. And those who are familiar with random forest, they will feel familiar also with that command. Well, the rest is only beautification. We have to bring back, we get the classified map, and we have to reassign the categories. So that is the legend, basically. Yeah, there's a category copy command, and this we take simply from the training map, because from the training we had all the explanations inside, we assign it back. And then we can visualize the result. And that results will look like this. So if we now compare it to what we got, it's not totally identical because the map is different. Say the input data are different. And remember, we only used mean temperature, precipitation sums, and elevation. That's all. But I would say not so bad. Sorry, maybe I don't know how we see best Europe. Yeah, here are some differences. This is quite different here, but overall it's not so different. So this just as a non-scientific example how to do this machine learning stuff. So the rest of the lecture is just some linear regression and multiple regression here. I suppose that everybody is familiar with regression in general. Here you just see some tricks how to transfer variables in a session, in a terminal session from one command to the next in an easy way so that you can automate everything. Multiple regression is like, let's analyze the connection between latitude and temperature. And then you get here the results, and this is an implementation which is identical to the results you get with the corresponding command in R. And yeah, you can compare yourself which one you like best. You remember there's the R-GRASS interface, so you can also transfer your maps and read them in R and do the analysis there and write back the results with R-GRASS 7. That's up to you. So the overall message, know that these tools exist, and please pick the ones which you like best, which are the fastest, or giving you the best result in terms of quality and performance. So with that, I would like to close this session here, this morning one session, and I think we move on to coffee break. Feel free to ask, please ask and suggest. From Mundialis, so some processing with open source GIS, I brought postcards. These are Sentinel postcards. I will put them next to the coffee. Please grab them and enjoy. Thank you very much.